Dr. G. S. Mahalakshmi, Assistant Professor, Department of Computer Science and Engineering, College of Engineering, Guindy, Anna University, Chennai. She has more than 13 years of UG and PG teaching experience and 5 years of research experience. She has so far contributed 85 research publications, and her research interests are Tamil computing, artificial intelligence, text, and web mining. She is an active member in UG and PG Syllabus Revision Committee and designed the syllabi for Anna University and affiliated engineering colleges for the following subjects: software requirements management, software quality assurance and testing, artificial intelligence, knowledge management, object oriented analysis and design, and Tamil computing. She has also authored several books, 2 journal papers, 31 book chapters, 3 lecture notes, 3 international conference papers, 36 national conference, and 10 other papers. Dr. G. S. Mahalakshmi is an associate editor of Mimanjari, an official magazine on Tamil computing from INFITT. The books of Dr. G. S. Mahalakshmi are Kanithal Adipadai and Kanini Moriyiyal in Tamil language.
Welcome to UGC lecture series in computer science. In this episode, we are going to discuss about the fundamentals of memory management, which involves address binding schemes which are static, dynamic, and the variations in address binding. In address binding, fundamentally, there is one thing which is very important. The main memory and registers are together taking part in binding the addresses from logical addresses to physical addresses. In memory management, basically from the disk, the program must be brought into the memory and it has to be placed within the processor for further execution. There are fundamentally two variety of storages computer system, basically main memory and the registers. Registers are capable of storing only single bit of information, whereas main memory is capable of storing a large amount of data. Therefore, there has to be a mediator between the register and main memory to buffer the contents which are getting stored. This mediator is called the cache memory. This cache memory sits between the main memory and CPU registers so as to buffer the contents which are stored back to the hard disk or which are replaced from the hard disk to the CPU for further execution. Therefore, there comes the need for managing the files which are getting stored inside the memory. It can be a secondary memory, it can be the main memory. There has to be policies and schemes devised for managing this memory. The fundamental thing behind the policy is address mapping. There needs to be a mapping between the logical address that is generated by the CPU and the real physical address which is existing inside the memory. While this mapping is carried on, there can be a mismatch or a mistake which is done during the address binding. Therefore, there has to be a memory protection mechanism which ensures that there is no pitfall in the address mapping scheme. This protection of memory is actually done by two registers which are known as base register and limits register. Fundamentally, the base register cannot exist separately. It can only coexist with the limits register. Therefore, we always say the base and limit registers as base limit register pair or memory protection address register pair. These base and limit registers fundamentally help to define the logical address space. From this diagram, you can identify there is an operating system which is loaded at the top of the memory area and there are 3 processes which are loaded. Every process has its boundaries defined in terms of base register and limits register. In this diagram, the process 2, the second process, has its starting address as 30004 in the base register, which indicates that from this particular address, this process is loaded inside the memory. There is another address in the limits register 12090. This address indicates the extent to which the process can exist inside the memory. This 12090 can be calculated as a difference between 42094, that is the last address of this process, minus the starting address of this process. Therefore, every process is ensured the protection of memory with the use of base and limits registers. Therefore, there needs to be a binding between the address register pairs which are inside the memory. This binding can happen both with instructions and with data, and this binding can happen at 3 different stages in the life cycle of a program. The number 1 stage can be compile time, next can be load time, and the rest can be run time or execution time. Therefore, the difference between the address binding or the stage where the address binding happens actually defines the complexity and the performance of the program under execution. Therefore, to prepare a program for execution, there are 3 fundamental stages where the program is getting transformed. The first stage is translation, next is linking, and the next stage is loading, after which the program is ready for execution. These are the program transformations. So, assuming there is a source module, that is the code or the .c program which we are writing is mentioned as a source module here. So, the source module is converted to the object module and this process we call as translation. Fundamentally, during compile time, the compiler takes care of these translations in detail. Assuming we have written different such source modules and we are compiling all the modules together, during the translation phase, every such source module is getting converted to the object module. From the object module, there is another stage which is happening. We call this as linking stage. During the linking stage, many such object modules, if they have interrelations within each other or interreferences among each other, those references are linked together and the module which is ready for loading is getting generated. This stage we call as linking stage. After this stage, that is after having linked the interreferenced object modules, now our load module is now ready for getting loaded into the memory. A loader takes care of this loading operation. Therefore, during loading, our load module is loaded into the main memory, after which the execution stage starts. So, once the module is loaded inside your main memory, the actual program starts executing. There are 2 things which needs to be taken care of during the address binding. The binding can happen fundamentally statically or it can be happening dynamically. Statically in the sense, before generation of executable code, every binding is about to happen. Otherwise, if the executable code is generated, only then the address binding happens, means we refer to that as dynamic binding. Therefore, static binding is otherwise called early binding, dynamic binding is otherwise called late binding or delayed binding. We shall discuss static binding right now. In static binding, there are 2 varieties. Number 1 is compile time static binding. Compile time static binding, the name itself tells you that this particular binding is done during the compilation stage of a particular program. If memory location is known prior to the compilation time, the absolute code can be generated during the compile time. But there is one particular problem in compile time binding. Most of our programs don't have the absolute code generated because most of our programs are actually loaded in a different location than from a promised location prior to the compilation. This actually is a feature or a benefit of today's operating system. Therefore, static binding can be said as a feature in olden times operating systems, and nowadays hardly any operating system does static binding. And in that too compile time static binding. The next variation in static binding is load time static binding. In load time static binding, the binding is a little postponed, but it is done during the load time. That is, during load time, the binding between the addresses happens and the relocatable code is getting generated. The only problem is this load time binding has to generate the relocatable code if the memory location is not known at the compile time. Therefore, there is one primary difference between compile time static binding and load time static binding. In compile time static binding, if the memory location changes, it is of no use. In load time static binding, memory location can still change, but every change has to happen during the compilation stage itself. There is yet another variation in static address binding. We will discuss the address binding in detail. Here a source code is getting generated. The compiler compiles the source code as an object module, and the linker tries to link the source code, link the object module into the memory. During this, you can see in the code there is a function called f which is getting called, and in the object module the same call is getting translated as branch f. When the object module is getting linked to the memory by the linker, the function real definition of the function f is loaded from address 0 to 100, and the instruction branch f is replaced by branch 0, which means the f starts from 0. Therefore, when you want to branch to f, actually you have to branch to 0. So, this is actually done by the linker. While getting loaded, the real addresses are actually binded. Assuming the entire load module is loaded into the main memory starting from the address 1000, now the loader rewrites the addresses in the instructions, such as the branch instruction 0 now is replaced by 1000. The reason is the 0th instruction in the original place is now found in the address 1000. Therefore, the branch 0 is now translated to branch 1000. You can always refer to the previous instruction. Previously, the instruction was store 120, and because it is now starting from 1000, 1000 is getting added to 120, and therefore, the real address reference is now store 1120. This is how the address binding is happening. The next variation in address binding is dynamic address binding. In dynamic address binding, there is the execution time binding, otherwise called it as runtime binding. Here, the binding is delayed until runtime. This is an important feature in address binding. The number one flexibility is that the process can be moved during its execution time from one memory area to any other memory area. Therefore, the real address need not be known prior to the address binding. There is some flexibility given to the process by the operating system, but there is a difficulty equally which requires hardware support for carrying out this particular kind of address binding. That is hardware support in terms of base register and limits register. When the binding is postponed and done at runtime, the base and limits registers take care of the address binding such that the memory references should not fall beyond the limits of beyond the addresses in the mentioned in the base and limits register. Therefore, dynamic address binding is actually efficient in terms of faster processing and flexibility in generation of code. Most of the modern day operating systems use some or the other kind of dynamic address binding. However, there are many variations in dynamic address binding. So, the number one variation in dynamic address binding is the address map which is getting generated. We can refer to the static address binding which we discussed earlier. It is exactly the same except that here wherever we load a module from 1000 or 2000, we do not replace the addresses as 1000 here. We still retain the original address as branch 0, and only when the address mapping happens, this 0 is replaced as branch 1000, and this is how dynamic address binding happens. We will now go for a break and we will resume the lecture in short minutes. Welcome back after the break. We were discussing about the variations in dynamic address binding. We will now discuss about how a user program is getting processed inside the operating system. The source program enters the operating system and the compiler or assembler takes care of the source program, compiles it and generate the object module. The object module getting generated is given as input to the linker or linkage editor. Many such object modules will be there, so that the linkage editor examines the interreferences between the object modules and generates the linkable code which is actually called as load module. This load module is actually next given to the loader, such that the loader now takes care of loading the referred items from the system library and combines the user program and the system library components, and finally it prepares the program for execution. This particular thing is done by the loader, and therefore we call this as a load time process. After the loader loads the entire module inside the memory, the binary image of the memory is getting generated. We refer to this generation of this binary image as execution. So, during this execution, however, there may be some dynamic linking required. Such dynamic linkings are also made, and the final copy of the binary memory image is generated inside the operating system. This is how a normal user program is getting transformed from the source file to an executable file inside your operating system. Therefore, there are two important components inside your address binding schemes, which are logical addresses and physical addresses. Physical addresses are only real and logical addresses are not real. Logical address is some address which is actually generated by the CPU. Therefore, we refer to this address as virtual address, which does not actually exist inside the CPU. Physical address is the real address which is seen by the memory unit. The area or the address where your program is stored is actually referred to as the physical address. Logical and physical addresses are same in compile time and load time address binding schemes. The reason is, even during compile time and load time address binding, the address location is known prior to the binding. Therefore, these addresses will not be different, both are same. In execution time address binding, these addresses however differ. The real physical address may be binded to a different logical address during execution in dynamic address binding. Therefore, in dynamic address binding or execution time address binding, logical addresses varies from the physical address. There is a reason behind the mapping between the logical and physical address. In static binding, there is no mapping required between the logical and physical address. We said logical and physical addresses are going to be the same in static address binding. However, in dynamic address binding, due to the variation in the physical and logical addresses, there needs to be a execution address mapping which is done at the later stage of the execution, compilation and execution of a program, which is done by the operating system. Therefore, there needs to be a hardware device which does this entire mapping between the virtual to physical address and physical address back to virtual address, vice versa. This process is called relocation, the mapping between the logical address to physical address. This relocation is actually taken care of by a relocation register. The user program basically deals with logical addresses because user programs are actually mapped to the physical addresses and they are actually stored inside the memory. So, therefore, during storage physical addresses are real, during execution the logical addresses are coming into existence. This is how the relocation happens inside the memory. The CPU generates a logical address and the generated logical address has to be added to the contents of the relocation register and therefore the physical addresses is getting generated. This physical address indicates the real location from where the contents needs to be read from the memory. This is an example of a reading operation. For a writing operation also the same holds good. The value in the relocation register tells you what to add to the CPU generated logical address and therefore the addresses which are generated after the addition operation is the real address to where the contents from the CPU needs to be written to. Therefore, for both reading and the writing operation, the dynamic relocation has to happen inside the operating system's memory. This is how OS does the memory management efficiently. There are variations in address binding. In compile time, link time, load time and run time are the 4 fundamental variations in address binding, out of which the compile time address binding is absolutely the static address binding, which is otherwise called absolute binding because there is no difference between the logical and physical address here. In link time address binding, it can be static or it can be dynamic. In load time address binding, it all depends on the relocation register. In runtime address binding, it's purely a dynamic kind of address binding. The relocation register, overlays, paging, segmentation and there are many other concepts which can actually involve the runtime address binding. Now we will have a look at how normally a linking and loading is happening inside your operating system. This is how a main.c program which you, the user, programs is coded. The main.c is given to the GCC compiler, which is a C compiler, and the main.o object file is generated. The object file is given to the linker for linking with further files inside the operating system. At the same time, you must have used a printf statement or a scanf statement inside your program. Such printf or scanf are themselves a .c programs. They were already pre-compiled by the GCC compiler and the object files is already generated and is saved inside a static library which is part of the GCC compiler. Therefore, when we generate the main.o object file and submit it to the linker, the related printf.o files, object files from the static library are getting linked by the linker and the real a.out file is getting generated. This a.out file is not a binary image. This has to be converted. This is just a loadable module. This a.out file has to be given to the loader which takes care of converting this file into a binary image and it loads it to a particular location inside your memory. This is how the normal linking and loading happens inside your operating system. Now, we will discuss about the dynamic loading, how the dynamic loading happens. Dynamic loading means the routine which is called is not loaded until it is called. Only during call it is getting loaded. This is an actually advantageous feature. However, this saves memory, this has better memory utilization. However, there is no special support from OS is required. This can be implemented through the program design itself. However, often this dynamic loading cannot be used inside your operating system. This is particularly useful only during execution of large amounts of code inside your memory. For very small lines of code, if you use dynamic loading, the overheads involved in processing the dynamic loading will be much larger than the size of the program which is getting generated. There can also dynamic linking which can happen inside your operating system. That is, the linking can happen during load time or during execution time. It can be postponed until load time or execution time. Therefore, we call this as dynamic linking. This dynamic linking is done via the component called stub. Stub is a small piece of code which is pre-written and saved inside your linker. This stub is used to locate the appropriate memory resident library routine, and the corresponding linking is done only at the time of execution. The stub replaces itself with the addresses of the real routine and executes the routine. Until the replacement happens, the stub has its own dummy address written inside the code. However, there is one thing to remember here. There is a heavy responsibility inside your operating system's policies to double check whether the location where the stub would refer to really contains some amount of code for loading or linking during the dynamic linking or dynamic loading kind of situation. Therefore, if such routine does not exist, the postponement which is done will go totally waste. This is an example of load time dynamic linking, can relate to the normal linking. From the main.c, the main.o is getting generated as usual and is given to the linker, like how the normal way of linking happens. The printf.c is also precompiled and is saved in the library. In the normal linking, this library would be called as a static library, because the items from this library will be linked and only then the loadable module will be generated. But here there is a difference only in this area. The linker only links the necessary object files which the user submits and generates the loadable module. After the loadable module is getting generated, it is getting converted into a binary image and loaded into the memory. Similarly, the dynamic library will also have the binary images of this printf.o files, and only during execution of this binary image the necessary files from the library are referred and is getting executed. Therefore, imagine at the time of referring, what if the code in dynamic library does not exist? Your program, even though it is compiled and is ready for execution, will not execute. This is the one fundamental problem in dynamic linking. This is yet another variation of dynamic linking. Here the rest of the things are same as to generation of a.out file, and here also and up to here also it is same. The dynamic library actually houses the binary images of all these files. The only difference is here the loader is called during the runtime. Both are similar except one particular problem. Here the startup is basically fast. However, in load time dynamic linking, it only saves disk space. The startup has no difference between the normal linking and the load time linking. So, in summary, we can just say that in the lecture we have seen the difference between the logical address and physical address and the variations in address binding that is static and dynamic address binding, the concept of relocation, and how a user program is getting transformed once when it is loaded into the main memory until it is going for the execution. And we have also seen some variations and hardwares which are responsible for doing this address binding scheme. Questions. What is delayed binding? Where is the base and limit register contents maintained? Your system has thousands of processes executing simultaneously. Will there be 1000 pairs of base and limit registers? I would like to discuss the answer for this question. Even though there are n number of millions of processes inside your memory, the base and limit register, really there is only one pair of base limit register existing. The contents from the base limit register are written to a temporary memory area and it is used for further processing. This particular process we call as swapping, which we will discuss in the future forthcoming lectures. The next question would be, which is costlier to implement, dynamic loading or dynamic linking? With this we will end this lecture. We will look at the other mature topics in the forthcoming lectures. Thank you.